Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good afternoon, everybody. I think we're going to go ahead and get started here. Welcome to the final breakout session before the final keynote on day 2 of the Faculty Summit. I'm very pleased that you could all join us here today. My name is Alex Wade. I am Director of Scholarly Communication with Microsoft Research. And it was 1 year ago at this Faculty Summit that Harry Shum got up on stage and talked about the evolution or the graduation of a project that we've been running in Microsoft Research for a number of years called Microsoft Academic, and the fact that we were going to be moving that into full production in Bing and in Cortana. And several of the engineers and program managers here working very closely with Bing and Cortana have been working on that for the past year. And if you didn't get a chance to come and see at our demo showcase earlier today, do find one of us before the end of the day so we can show this to you. But it's been important for us, or it's been helpful for us to see over the past year an increased amount of activity in what has been called big scholarly data or Big Scholar. There have been workshops that Lee has organized with the IEEE Big Data conference last year. There's been activity at AAAI. There was a Big Scholar workshop at the WWW conference this year. And we're seeing this growing interest in coming to, this renewed interest in people coming to the scholarly data and moving beyond simple citation metrics into very large-scale endeavors. And it's great for us to see it. It's great for us from a talent pipeline perspective. It's great from a collaboration perspective, and just a diversity of ideas for people coming into this space. So welcome to all of you. If you do have the chance, we're also going to be running a half-day workshop tomorrow in this same building and getting much deeper into this area. So thank you. With that, I'm going to hand over to my co-host, Yang, who's going to introduce the forum today and introduce our speakers. So thanks.
So welcome to our session. My name is Yang Song. I'm a researcher at ISRC, Microsoft Redmond. So today we are honored to have 4 different speakers from different organizations. So we plan to ask them to speak about their great work for about 10 to 15 minutes. And after that, we will do a Q&A sessions. And after that, you see all those chairs here. So we'll do a panel discussion. So without further ado, the first talk is brought to you by Professor C. Lee Giles from the Pennsylvania State University. And Professor Lee Giles started CiteSeer at NEC Lab in 1997, which was the first Scholar search engine, like website Scholar engine at that time. And later on, he started CiteSeer X and brought that thing to Penn State. I remember when I was still his student, half of the traffic that comes to Penn State goes to CiteSeer. So which was a very interesting topic at that time. And half of the security breaches also happens to CiteSeer as well. So I'm not sure if he will cover anything like this today, but I'll give it to Lee.
Is it on now? Okay. Is it on now?
Can anybody tell? All right, it sounds like it's on. So thank you very much for inviting me. It's great to be able to come back to Microsoft Microsoft Faculty Summit. So it was really nice to be here again. I haven't been here in a while, so I've always enjoyed it when I come here because I get to learn so much about the nice things that Microsoft is doing and also other individuals like myself are doing. So this work has been funded in part by NSF and Qatar. And in the past, it's been funded by Microsoft Research, and it's also been funded by NASA. So what I'm going to talk about today is scholarly big data and some insights that we have. What I hope to give you an idea of is how big scholarly big data is, just from some measurements we've made, and quickly go through some applications that we've done with scholarly big data that we're encouraging you. We're saying, look at these sort of things you could do, and you could do them too. Oh, we have lots of collaborators. If you don't see your name up here, it is. It's others. So, this just the CiteSeer project is probably, I think we had a count recently. It's generated about 100 papers for us under the things that we've done. So it's been a very productive experience for us. And by the way, it's really great to have one of your former grad students introduce you. It's like a real treat. So these are some of the projects, by the way, that we built, some of which are living and some of which have died, and some are on life support. So let me just get to the point. What is scholarly big data? So we're trying to figure this out ourselves. So we define it in a very general way. It's all academic research documents, journal and conference papers, books, theses, TRs. So it's a fairly general thing, but in some ways you know it when you see it. Sort of like other things you know when you see. And then you could look at a lot of related data, like lab web pages, funding agency and organization grants, records, and reports. That's actually very important. And it's being used quite a bit for science-to-science research. Then you can look at patents. And then there's actually a lot of associated data, like PowerPoint presentations, experimental data, video of course materials, others. And then, of course, there are a lot of social networks. And there's really many instances of scholarly big data, and which is great to see, because when we started doing this, there weren't that many instances. And it's nice to see all these sort of take off, each going in various directions. So what does it look like? Well, it doesn't look like this. It looks more like this. So it has a lot of graph structure to it, and we want to be able to take advantage of that graph structure. So where do you get this? Well, we like to go to the web. And I'll talk about, but you can also go to repositories. You can get it from us. We give our data away. You can go to various resources like PubMed and DBLP. You can go to laboratories. Sometimes you can get it from publishers. You can get it from some aggregators, but usually this is not as easily available. Patents, thank goodness for the APIs of Microsoft Academic Search. This is a great place to get it. But one of the interesting questions is how much is there and how much is freely available. So we did this estimate of scholarly big data. So we used 2 public academic search engines to estimate the size using capture, recapture, or you might know this as Lincoln Peterson. It's a standard technique that's been used, it's been around since the 1880s, used by population biologists to estimate a population. And we first used it when, in our science paper in '98, when we estimated the size of the web. So we find a paper that both search engines have from Microsoft Academic Search and Google Scholar. We extract the list of citations for that paper. Both search engines compare overlap. So we say the list of citations is representative of the coverage of a search engine. And using the size of one search engine, you could estimate the size of the other. And by the way, this is limited to English papers only, papers in English, but there's been a recent estimate on papers in other languages. And by the way, this is just the technique for doing this. This is just the mathematics. But because we assume the conditional probability that a paper would be more likely to be in sites to Google Scholar if it was in Microsoft Academic Search, you can say this is a lower bound, because that seems reasonable in terms of those probabilities. There is a random sampling assumption, but we can sort of ignore that in some ways. And this is what we found. Actually, it was freely available based on the various types of research efforts. I mean, the various classes of areas as defined by Microsoft Academic Search. The nice thing to know is, look how good we are. You know, we are a really good field in terms of making our papers freely available. We still have some work to do. By the way, this is just percentage. Physics is very good too, and surprisingly, economics and business is quite good, because the economists have their own academic search engine called REPEC, and they put a lot of their papers out there because economists don't publish a lot of papers. So they write these tech reports and they circulate them and get comments. So this paper, so what did we come up with once we did this number? Well, we found a lower bound of at least 114 to 120 million scholarly articles available on the web. This number varies depending on what assumptions you make when you do a Lincoln-Peterson. At least about a quarter of them are publicly available, about 27 million. I just pointed out how good we are. Google Scholar has about nearly 100 million of these. And so Google Scholar doesn't have all of these. So there's a lot of things we could do next if you wanted to do this. One, you could distinguish between publication types. You could do more estimates. You could do a longitudinal and geographical study, which we think would be really interesting. You can look at duplicates. By the way, we didn't find many duplicates, at least in our analysis. And you could do languages besides English. And this is the paper that you can find in PLOS One. This is really neat. Nature actually did an article on us after we published the paper. After they rejected the paper and told us that they would do a news article on it, which is nice because they did. And so we did get some very good press on this. So what would you do with this? Well, some of you might be familiar with the FUSE program. Is anybody here a part of the FUSE program? Okay. So this was a program by IARPA, which was finding patterns of emergence in science and technology and look at trying to predict scientific directions, discoveries. And so this actually used the kind of data we're talking about. And sort of the idea was to discover patterns of emergence and connections between technical concepts. So this is sort of the thing we would want to do too, right? I mean, why should this be restricted just to this type of study? So now I'm going to switch and tell you, if you have this data, what can you do with it? So I'm going to try to give you some ideas of the things we've done with it. So we have this collection of tools that we've been working on for at least about 8 or 9 years. We call it Seer Suite. So it's a suite of seers. And these are open source toolkit, and you can build academic search engines and related things with it. And these are some of the ones we built. Notice CiteSeer has a superscript, and ChemSeer for chemistry has a subscript. Why does it have a subscript? H2O. Okay, so the chemists really like this, right? They know it's for them because they get that right away. And then we've built others that I'll talk about briefly. And so this is based on Soto-Lucene MySQL. And the features that we offer are automated, specialized metadata extraction. The system that we've put together is fairly modular. You can bring things in and out. You can put other tools in there. And so these are some of the information extraction that we've done, and I'll talk about them briefly. Entity disambiguation, knowing how to disambiguate authors, tables, figures and graphs, chemical formulas, equations, author ethnicity detection. And these are some of the engines that I'll talk about very briefly. I might talk about all of them. And by the way, I think they're all up. This morning they weren't. We had a terrible crash. Something else that's interesting is when you do this kind of research, you can actually publish this kind of work in places that you might normally not think of going, like in the systems world. So we have 2 Usenix papers. We have an IC2E paper. So the reason is because these fields like real systems, and this is a real system that's up and running. Okay, all right, so I won't say much about this, but these were the guys that were the initial developers of CiteSeer. They've done quite well for themselves, except for this guy. He's an academic. But the other, that was a joke, sorry. So it was a very early project. It was hosted at Princeton at the NEC Research Institute, and then it moved there when, in some ways, it did a lot of very unique things like automatic metadata extraction, citation indexing, reference linking. And we think it's one of the first scholarly search engines. I mean, it seems to be that. I'm sorry, did you show that back again? 5 minutes, thank you. And it shares data. So it crawls the web, does active crawling for researcher homepage and archives. Right now, this week we broke 6 million documents. So it's a little bit out of date. We have millions of files. We probably have 100 million citations. We have about 13 million author mentions. these are mentions, and then depending on how you believe in our disambiguation, we have 1.3. Disambiguation is always a funny thing. And we get 2 to 4 million hits a day. We're the most attacked site at Penn State, but we're not broken into, but we are the most attacked site. We add about 100,000 documents monthly that we think are unique. We have about 300,000 documents that are downloaded monthly. Based on IP, we have about 1 million individual users, and depending on how you count, we have about 40 terabytes. And you can see that our usage is from a lot of places. So we do a lot of focus crawling. I'm going to briefly skip this, but it's very important to have a really good focus crawler to go out and get these documents. We have a whitelist and blacklist policy, which I don't have time to talk about, but a lot of this is discussed in these papers here. So we do a lot of AI machine learning methods in our extraction. And our recent IAAI paper describes this. It's a very good description of what methods we use. And we do it for all kinds of extraction. And we also use it for author disambiguation. So this is sort of, so this is sort of our extraction model where we take PDF, we convert it to text, there's all kinds of converters, and then we apply all these algorithms to get all this stuff. And then once you get this stuff, you got to index it and look at it. And what's interesting is we've also worked on how you take this information out of some of these features. So this is one of the first things we did with tables. This work was funded by NSF Chemistry. We were building a chemistry search engine. And one of the first things our chemists asked us to do was to extract data from tables. And we asked, how do you do it now? Well, we send the grad student over to the library, and they type it down in their computers. Whoa. So we said, OK, that's an interesting thing to try to do. So we built a table extraction search engine. A table finder finds the tables and extracts data from the tables. It's not perfect, but it's not too bad. And I believe that there are others out there that are a little bit better. What about disambiguating all these authors? This is an algorithm that we think is pretty scalable. It uses some old DB scan methods in which we learn the distance. You can use various different learning algorithms on the distance. The one we use right now is random forest. Does it scale? Well, just recently we did 80 million mentions. We just scaled 80 million mentions in PubMed. So we know it scales. And we've given this work to some of our colleagues in Science of Science. This is an expert seer. This was actually funded by NSF slightly and Dow Chemical, because Dow Chemical is interested in chemical search engines, because they have, this is what they do. And this is the kind of thing you can build if you have the data. You can do expertise. You can do expert searching. So in this case, the work we did with Dow Chemical was they were going to look at their large collection of documents which they want to know a lot of information about. And this was published, the best discussion of this was in JCDL recently. And this is sort of what you can do, this is sort of what it looks like when we do recommendation, and based on the sort of things that we find associated with this term. We did a CollabSeer. We want to do collaboration of collaboration. Excuse me. This is a collaborator of a collaborator model. So we recommend who you should collaborate based on who they collaborate with. And this was funded by Alcatel-Lucent. And this paper, there's a description of this in JCDL. There's other papers on this too. It's up and running, at least it was. And it uses a friend of a friend model, so it's actually a variation on a triple, right? A Wij-K. So, but to make that scale, you have to do a lot of approximations. This is something we're working on right now. This is a hard problem. This is automated figure extraction. So our chemists, this was also funded by NSF Chemistry, they said, we want you to take data out of figures, plots in particular. All right, so how do you do it now? Well, when the grad student goes over to the library, they not only take their computer, but they take a ruler. And they measure the distances of those points on the scale and write that down. So that's a very interesting problem, right? But we're still working on this. This is a sort of in progress. We've got the extraction of the figure out right now. And to show you, you think, yeah, you can do that, you can do that, you can do that. No, this is very difficult. So these are the things we think we can do. We've done some examples of them already. We have quite a few papers. Our most recent paper will be delivered in Switzerland in September. And just to give you an example of some of the algorithms that we've tried out for doing this, this is pretty sophisticated, right? I mean, not sophisticated, complicated. It's got a whole list of things that it does. We have an automatic recommendation system. You can now put in your paper, document your papers, and you can put the full paper in, and we recommend citations for you. This can be quite useful, especially if you don't want to miss citations. And you can actually tune this so that you can get the most contemporary citations. When we first had this up and running, one of you, maybe not here, put in "the" to see if you could break it. And it did break, but we fixed that. So it's always useful to build these things up and see what people will do. And so these are some of the publications, the most recent ones in AAAI. And Wenyi is here. He's an intern at Microsoft this summer. So this is probably the most interesting thing. We tried to integrate all this together. And I probably am out of time. Maybe I have a minute. All right, so we tried to integrate all this together where you have papers, authors, tables, figures, formula, extract tables, collaboration. And this is sort of the thing we did for chemistry. And doing this integration is still a hard problem. It's really hard to know how to do the ranking for putting all this together. So I'm now summarizing. A 250,000 documents are freely available. There's 120 million records out there. Total online estimates, a lower bound. There's billions of citation mentions. There's hundreds of mentions of tables, figures, math, formula. There's a lot of stuff there. Challenges. How do we effectively integrate this? This is still an open issue. We're trying to figure out how to integrate all this data. Natural language generation. Can we actually take this data and create, and this is an active field of research where you take data and you create language about what this data means. What are the ontologies? Can we, and we'll hear more about this, can we have a scholarly knowledge vault? And then there's this new program called Big Mechanism, which actually tries to do a lot of the things we're talking about here for problems in medicine. And so there are many issues that we can go through. Petabytes of data, billions of objects, very rich content. Applications are more common than a lot of people realize. There are many sort of AI and machine learning can be very useful. Observations, there's a large amount of growing scholarly data. Big scholarly data creates new research opportunities. But this is something you always want to keep in mind. Big scholarly data creates other big scholarly data. As soon as you get it, you start doing more stuff with it. So now your 40 terabytes is 80 terabytes, and it keeps growing and keeps growing. You've got to back it up. So just keep that in mind when you do these kind of projects. So I think this is a good place to stop. So thank you for your attention. I rushed through that, so I'm sorry, but I just want to give you a taste.
You're not following the rules here. We are going to hold questions until the end there. So we're going to run through the speakers, and then we'll save questions.
Okay.
Thanks. Go ahead.
Okay, thanks for the great talk. And our second speaker, his name is Jie Tang. He's a professor from Tsinghua University in China. He actually started one of the biggest scholar search engine in China called ArnetMiner, which has approximately 80 million collection of papers right now. And I think today he's going to talk about something about the next version of the ArnetMiner. So,
okay, so yeah, thanks for the invitation and also the introduction. And today I will introduce the second generation of AMiner. We called it AMiner before. Actually, the name was ArnetMiner. So we called it a second generation. So first, I want to use another slide to quickly go through the first generation and also the history of ArnetMiner. So it works. Okay, so this is actually so ArnetMiner was launched in 2006, and actually there are 4 stages for ArnetMiner. And in 2006, this first stage actually focused on extracting the information from the web. For example, we extracted the research profiles, and also we integrated data from different sources like DBLP and also ACM and also some other sources. And also we try to automatically identify the research interest, the first stage. And from the 2009, the second stage, we try to understand the semantics of the content. For example, we develop methodologies to extract semantic topics from publication data, for example, publication papers. And also, we try to understand the academic communities. We try to understand how communities change over time. And the third stage, that is 2010, we try to develop a method for network. For example, we develop methodologies to automatically infer advisor-advisee relationship automatically. And also, we try to use the network information to automatically recommend the reviewers for papers. Okay. And also, this method actually was used by many conferences. And the last stage is 2013. At this stage, we develop a platform for users, so everyone can develop some applications. For example, geographic graphic search and also collaborator recommendations on the platform. So that is the first stage of the first generation of ArnetMiner. So today, I will introduce a second generation of ArnetMiner. We call it AMiner. So I guess you already say that here, first generation, we called it ArnetMiner. So the name was just a bit complicated. So not everyone understands the name. So the name actually is Academic Researcher Network Mining System. So just to help everyone remember the name, so we changed the name to AMiner. So that is AMiner II. So we try to understand the semantics of the big scholar data. So when we want to understand the big scholar data, when we want to understand the semantic information, so everyone knows that we face the big data. But the big data itself is not valuable. Only if we understand the semantic information or we try to extract the knowledge from the big data, we can benefit from it. So what we try to do is that we develop AMiner II. The system actually has 3 subsystems. The first one is, we call it social network extraction. That is to extract information from the web, from the different sources. And the second subsystem is social network storage. That is to store the data into a database and also how to build a fast index method. And the third one is modeling. We call it academic network modeling method. And based on that, we provide different search functions like expert search, and also person search, and also topic browser, and also some other functions. So just to give you some example, for example, person search, if you type a person name like Javi Han, and then you can find such a profile information. And here you will see we have some basic information extracted from the home page, and also we have some citation statistics, and also research interest, and also ego network. And here you will see some advisor-advisee information. And also, we integrate some information from different sources. For example, from video lecture, we provide some video information. And also, we integrate information from some patent website like patents. So that is person search. And also, if you type some keyword like data mining, and the system will return some experts, like data mining experts. And here you will see some more interesting information. For example, for every researcher, we just identify the demographics information, like gender, language, and location, which means that you can find, for example, you can find some person working in United States, but the gender is male or female, but he can speak Chinese. Okay. And it's very interesting. We also integrate knowledge information, for example, the Wikipedia information from the about the data mining. And also we integrate some Chinese information, which means that if you type data mining, we will provide some Chinese data mining, like 数据挖掘, okay. And also we provide some ranking information for ranking service, for example, organization ranking. And for example, okay, if you just define the computer science, you will see that, okay, Microsoft is the first place, okay, for, computer science. Okay, and also I highlighted Tsinghua University is there, 26, okay. And also we provide some, deeper analysis for the ranking. For example, we can visualize the results. And here is the Microsoft, and in different conference, top conference. And also we have the conference ranking. And here is the conference ranking. Actually, it's not conference ranking because it also includes some journal information like science and also some transaction. And if you click every publication value like conference or journal, and this system will return some detailed information like keywords and also nationality. I mean, the author from different countries, and also the person can, and the author speak different language, and also the top cited authors and top cited papers. And also we have the reviewer suggestions, like if you input a paper, and the system will provide some function to and recommend some reviewers by avoiding some, conflict of interest, and also load balance, and also some other information. So, and also actually it's more interesting is that we integrated this reviewer suggestion function into Scholar One, and here the left side actually is Scholar One. And if you download this app, this is the app, the right side actually is the app which can directly recommend some reviewers to this paper. Okay, so this can help. Associate editor. If associate editor of some journal, of course this journal must be managed by the Scholar One, and then you can download this app, and also you can use this app to recommend some reviewers. So far, actually, AMiner II already have, since 2006, we already have about 40 million research profiles, and also nearly 8 million publication papers, in total. And also the number of users actually comes from many countries. Like in total, we have more than 6 million IP accesses, unique IP accesses from 220 countries and ranges. And this is the top 10 countries, including United States, and also China, and also Germany, and also some other countries. And today, today, actually, I just want to quickly go through some technologies, quickly go through. And mostly interesting, I want to say some recent progress. Because in this system, actually, we want to extract the semantic information and to populate the semantic knowledge base for Scholar data. But before, actually, if we talk about this, you will see that we want to develop some methodology based on machine learning and data mining algorithms to extract information from the web or extract some detailed information from the Scholar data. For example, if we want to have some Scholar data, if we want to have some semantic information for each researcher, basically we want to extract some semantic information to construct some structured data for each researcher. For example, here, we can extract some structured data for this researcher, including some contacting information, educational history information, or academic services. And also, we can integrate some information from some other sources. And actually, we did that several years before. We just built a database more than 1 million research profiles. And we see that this is, successful. But the question actually is that, is this enough? So actually yesterday, after a keynote, I just searched the GNet in our database. I found that, this information, I have to say that our system automatically found the CMU profile, CMU homepage. And I Googled it. I found that the CMU homepage is still the first one. And all the information was correctly extracted. And you can say that the algorithm is good, but unfortunately, the data, the semantic data is out of date, right? It is still CMU professor. And if you continue to see some other page like LinkedIn and also some other Wikipedia page, you will see that, the required semantics information actually are distributed in different sources, And also, most importantly, all the required information are already structured. We do not need to do the extraction, So the problem actually changes our challenges. Before, we just want to develop a method to extract the information, but now actually is that, we already have some semantic information, but the semantic information are distributed in different sources. What we want to do is that, we want to integrate the semantic information together. To ArnetMiner, actually, we want to integrate the information from LinkedIn, video lecture, and also Google Scholar. That is what we want to do. Actually, today we just tried a different search engine. Some researchers just say, my profile is already there, is already here. You do not need to extract information. You just point me to this page. That is the most important. So what we want to do is that we want to collect the different social network with different information. Okay, so we just develop a method. I guess I want to skip some details, technical details. If you are interested, you can go to our KDD paper this year, and accepted by KDD 2015. So what we want to do is that we develop a method, COSNET, and which is an energy-based model to just formulate this problem into an energy-based model. So actually what we have done is that just given different networks, so we just consider the local consistent, the similarity between different profiles, and also we consider network matching, and also we consider global consistency. We just try to avoid the global inconsistency, and then we just develop a method to consider all the information, and we have a objective function by consider all the information together. And also, to solve this problem, we just try to use a maximum margin learning method. And also, this method actually is intractable. So we just use a Lagrange relaxation to decompose the original objective function into a set of easy-to-solve subproblems. And then, to solve this problem, then we can use some kind of algorithm, for example, projected subgradient. And then we have some results. For example, we just try to collect AMiner with different social networks, like LinkedIn and also video lectures. And you will see that our method, COSNET, the performance is much better than some other algorithms, like lane matching, SVM, and also some other method. For example, Sigma. Sigma was an algorithm developed last year, and also published last year on KDD, which is to integrate different networks and also leverage some kind of method like local propagation. So, and also here is some other results. For example, this page, and we will see that all the information actually, the contact information was replaced by LinkedIn profiles. And if we can find the LinkedIn profile. Okay, and also some other information like video lecture and the USPTO, we have all the information. So to summarize, actually, ArnetMiner today, we already have more than 10 versions. For example, starting from the 2006, and we have more than 10 versions here. And also, so far, we just focus on network integration. And also, we apply the deep learning to just mining the content information. So that is what we have done. And also, the system actually has been widely used by different publishers, for example, Elsevier, and also some other conference like KDD, and also Wisdom, and also some other conference to generate the PC member or some other organizer's profile. And also, most importantly is that AMiner has been developed as a platform. So it is not just a system. Actually, we can apply the platform to different data, like patent data and also social network data. We call it QQ miner because we apply the platform to some Tencent data. QQ is popular in China, so it was a product of Tencent. Tencent is the largest internet company. Yeah. Okay. So, and also we have many opportunities to collaborate with different companies and organizations. And here is some representative publications on KDD or some other conference. If you're interested, you can check. So that's my talk. Thank you.
All right. So thanks, Professor Tang, for the talk. And our third speaker is Oren Azioni, who was until recently a professor at University of Washington across the lake. And he's now a CEO who runs this fantastic institute called Allen Institute of Artificial Intelligence, or AI, or AI 2, or AI squared. So I think today he's going to talk about something that they have been doing recently at AI 2. So.
Okay, thank you very much. And we are a new institute in Seattle. And at this point, we're about 40 people and still hiring. So first of all, if you're interested, come talk to me. And also my colleague Vu Ha is the lead architect on this project. But putting the commercial aside, what I wanted to say is, first they said, oh, do you mind going third? And I was like, no, it doesn't matter. But I'm the new kid on the block, meaning our academic search engine. iIdeas, we're actually about to launch at the end of 2015, and we have these great projects from 1998 for 2006, and it's all this richness. It makes me want to just sit down and say, what do I have to say to you? So what I will do is I will be brief, and I will also just acknowledge that something that's really nice in this area is that we've gotten to already build and collaborate. So Lee Giles is kind of the father of this subfield, shared with us his data, and Alex from Microsoft has shared with us some of their data, and the AMiner folks have also been generous, and we've exchanged information. So it's really a wonderful thing, right? Because this is about big scholarly data, open data, and so the more that we can share with each other and follow really Lee Giles' vision, right, of building something that puts the pieces together, the better. So what is it that we're doing at AI2? The emphasis, and it might not surprise those of you who've known about my work for a while, is we're trying to leverage machine reading, or in less fancy terms, information extraction into driving features here. And everybody talked about that to some extent, and we've got our own version of that. And our focus is, more than anything, to take the basic questions we have and deal with information overload. Right? So it's a little bit different than AMiner, for example, where there's all these cool visualizations and additional information. We're in some sense a little bit more minimalist, right? We're trying to give you less, but allow you to home in on the papers that you want a lot faster. So that's the theme. And right, we all know all that stuff. And again, the basic pipeline that we use is not any different than anybody's, except that, again, I want to highlight our collaborators. Lee Giles and his team gave us a huge amount of PDFs to get us rolling. We've been working with Andrew McClellan at UMass on some of his extraction work, Doug Downey and his group on key phrase extraction, and Marty Hurst has also been giving us guidance on the search. So again, continuing with this theme of a collaboration. And what I thought I would do, which hopefully will work across the internet here, is give a quick demo of our, again, as of yet not public system. And it'll be a very short demo if it's not up, so or if the internet is not cooperating. And of course, I don't know how to use Surface or whatever machine it is here. Stick around for a sec. So I just need a browser, I think.
Oh, we don't have a browser. Oh, here you go.
No, don't go yet. I'm worried that something bad will happen. Let's see. Okay, so this is not a public URL, and but we will be releasing this by the end of 2015. So here's the idea. You do a query like dependency parsing, and no big surprises here, except that one of the things we focused on, which is surprisingly hard, is getting the metadata out of these papers with high accuracy. So let's say I'm looking at dependency parsing, and I want to focus on Noah Smith, who is here and who's just recently moved to UW. And I already, even with our limited corpus and even just focusing on him, I get 129 papers. Let me drill down further to EMNLP. And just with a couple of clicks, a quick query and a couple of clicks, I've gotten it down to 19 papers, much more manageable. And yeah, then I can find, oh yeah, I wanted his famous turbo parsers paper. And we can start to look at what papers cite at. We start to surface citation context. Another thing that we're putting in very soon is the ability to distinguish between which of these citations, our papers these days have so many citations. A lot of them are throwaway citations, right? They cite it out of politeness or in a list of 20 papers, or they say things like, I love this one. See this paper, right? See Martin et al. 2010 for further discussion, right? That's not very helpful information. That's what I would call a throwaway citation. So we're going to be filtering and re-ranking these based on quality. So you can you have this paper that's been cited 500 times. You can home in on, again, what are the key and most interesting citations. So that's where we are now. We have a ways to go, but we're working hard to launch a computer science search engine by the end of the year, and I hope that you'll all use it. And I'm going to give you a place where to sign up to be notified when it launches at the end. So going back to the talk, which wound itself back a little bit, I also just wanted to mention we are also very interested not just in NLP, but in extraction of figures. Like Lee said, we've actually already released some open source software on automatic figure extraction. A lot of the information, as we mentioned, is in figures and graphs. And then we're able to classify the figures different types and start to actually extract the semantic information. So the idea is in the not too distant future, you'll be able to ask a query and the answer will be based on the actual curves in the figures, right? Not the text. And it turns out, again, the easy cases are easy. Like here's a red curve and a blue curve, it's really easy. As Lee showed, there can be a lot more complicated cases. The curves are in black and white. They're intersecting. We need to understand the captions. We need to understand whether the axis is linear or logarithmic. Surprisingly tricky to understand a simple figure. What I want to show you next, again, and I'm going to keep this very short, is some of our vision of where this goes in the future. So beyond just key citations and some of that metadata like author and venue, we're looking at, can we identify what is the problem being solved by this paper, what are the different techniques, and what are the data sets being used. Think of the stuff you see here on the right. Do I have a laser thingy? Yeah. And it is... Okay, yeah, I was worried that was the power and everything. Okay, so basically you can think of this as kind of an info box for the paper, right, where we take what's in the text and create a more structured representation of the basic. These are the basic entities that then we can identify the basic relationships, like, on this problem, this data said this technique got 73%. And other than just surfacing these as a quick summary, you can imagine starting to do queries, right? And in computer science, this is kind of fun. As we get broader and broader, think about a medical domain where you can start asking, okay, what are diabetes treatments that are 20% more effective than the one they had in 2014, in particular for middle-aged women, right? And there are all kinds of scenarios like you going to a doctor where that can make a big difference, because with the information overload, as we all know, our doctors don't actually have the latest information. So we're starting with computer science and hope to expand in concentric circles. Let me show you a little bit. So these are unimplemented mocks, but show you some of our vision for the future where we think these capabilities can go, building on information extraction. So let's say I do this query, information extraction. One of the ways that I can have completion is not just statistically as in Google's autocomplete, but based on the notion of, okay, I've got information extraction, I've got different techniques that I can use associated with that. And I can even surface how many papers are associated with this. So if I start with information extraction, I can quickly be guided. Do I want to look at that using Gibbs sampling, using conditional random fields, what have you? The next step is to think about aggregating extraction results across quite a number of papers to summarize the field. So let's say I'm new and I've heard of this information extraction thing, or I haven't been keeping track of it. Maybe I'm, Ray Mooney. I helped to create the field, but I've been doing, I don't know, vision and language more recently. And so I kind of want to check up on information extraction. So I'll type in this query, and I'll see a summary that says, okay, here's how it's progressed over the years since I got the field started. These are the different techniques that were used. Here are the precision numbers being reported in, let's say, relation extraction associated with these techniques, maybe on standard data sets that might be surfaced. And if I'm interested, right, okay, let's see what's going on with Gibbs sampling, I can click in and see what's called the provenance, right? I can go to the paper, the sentences, the figures that give me the relevant information. let's say, okay, so I looked at that and I say, yeah, Gibbs sampling, that sounds like pretty good stuff. So I can type that in. And again, let's say, well, let me get a sense of the overview, what people are using Gibbs sampling for. And again, another cut of the field extracted from a large number of papers. I can see here's a particular technique. I know it's a technique. And here are the different areas where it's being used. Maybe the size of the circles tells me how frequent it is. The point being, right, that as you can see with these mocks, we're shifting from this mode of I have a query and I find a paper, or I find 10 papers to read, right, because we're all too busy tweeting and Facebook and what have you. Who's got time to read papers? And instead I'm starting to get more of an overview, which can be helpful either to a new student, somebody who wants to get an overview, or to help you drill down to find the right paper, right? Even if we're the most diligent, right? We can't read all of them. There's just the acceleration in the production of knowledge. So again, I choose here dependency parsing relative to Gibbs sampling. Out pops a key paper in the field, and it tells me the results that we got. Here's what they look like in a diagram, in a table, et cetera, et cetera. So, you know, there's lots more of these that I can show you. I'll skip it in the interest of time. Really, the bottom line is that that's our vision, very distinct from what we're able to deliver. What we are going to deliver this year is a working, free search engine. If you're interested in being notified, please sign up here, alani.org, Semantics, Scholar.html, right? Sign up for launch. And want to, you know, join the colleagues and friends in this adventure. Thank you very much.
Thank you. We'll bring up all the speakers to the front, and they will dance, I guess. So.
Dance contest? I'll go last.
Yeah. You start first. You have a nice T-shirt.
I know Oren was chomping at the bit to ask a question earlier, so we'll let you go first. Make sure your microphones are back on. Each of you?
Mine on.
Oh, you lost yours. Here you go. Thank you. Okay,
So,
great. We also have microphone runners, and just like the other sessions, we will ask that you wait till the mic gets to you because we are recording this for posterity. So.
Oh, in that case, I'll change my question. No, I'm just kidding. What I wanted to ask is I was surprised by the numbers you were showing as far as free and kind of behind paywall, less accessible publications in computer science. And the reason is that in my experience doing a lot of searches, I really can't think of a time where I was looking for a paper and I couldn't find an open, publicly accessible PDF, which is quite different, right? Even so from the 50%. So I'm wondering, how do you account for that?
So that's a really good question. Am I on?
Yep.
Yeah, okay. So that's a very good question. One thing that you have to keep in mind is if you search from a university site, you often have complete access to various publishers, and you have to take that in consideration when you're looking for those papers. So a university like Penn State or UW, we have really good access to those papers, and that also comes up when you want to do crawling. You have to make sure when you crawl, you don't use those IPs that will allow you to go and get information from those publishers. Another study, there was a study that was reported in Nature last year that said, based on their own analysis of open access, that half of all papers today are open access in terms of freely available. So by freely available, we mean it's not behind a firewall if you don't have special access. And at least that's been our experience. There might be others who have other experiences on that.
With you.
Okay. Yeah, I mean, is that what you've observed in terms of open?
I guess in the university, it's very easy to access all the data.
Yeah.
And also for me, I have to say in computer science, if we want to find some full text, actually it's very easy because you can use Google Scholar and Google just to find the full text. And I mean, but from some other perspective, for example, from company or some other researcher, or from some other researcher from different fields, they want to find a paper actually is difficult.
Right.
I mean, yeah.
And also just to elaborate a little bit, keep in mind that our analysis was a lower bound, right? I mean, we're not saying that there's not more.
Yeah.
So something else that we found is that when you go, you have to look at, often we're looking for newer papers. Older papers are much harder to find. So that's why it would be very useful to do a longitudinal study to see if that the study done by Nature, reported by Nature, which was, not I would say not statistically as good as some of the methods that we've been using to just validate that study.
Johan in the back.
Yeah, so at the danger of sounding like that annoying reviewer that complains you haven't solved world peace and hunger, what struck me in all of your presentations, and I don't mean this as a criticism or a challenge, I'm just bouncing the idea off and see how you feel about it, but a lot of what you've discussed is actually sort of ways of discovering information that already exists, right? So I was thinking, for example, RefSeer would alert me of a citation to my paper, but what I'm actually most interested in is citations that don't exist but should exist. To give you an example, right? So it very often happens I'm asked to review a paper, and it's obviously relevant to my own publications, but they fail to cite them for. So the same kind of applies to articles, right? Some articles should have been written but haven't been written, right? So I just wanted to know how you see. I mean, that to me sounds like a sort of an obvious research front that is both very sort of a goal that is very different to achieve, but seems quite necessary to have. Otherwise, you're essentially looking backwards in time. You're always looking back at information that's already been created and cataloging it and making it easier to be accessed, but you're not really sort of pushing the boundaries of that existing knowledge.
Who wants to take the first shot at that? Just one shot. Not everybody has to answer.
So I'll just mention there is this term expected citations. And so, however, expected citations is usually only for citations that exist. but it's a measure that's been used in the past to try to figure out how citations will progress. It could be the case that you could combine some of the expected citation models to say, I expect some citations for these kind of topics. I mean, and we've seen studies of that, right? We've seen those famous studies where you look at these key phrases, and this key phrase is going up, this key phrase is going down, and then there was this famous one where the key phrase went down and came back up. So, and that was in security. So we could see those sort of things maybe with these kind of algorithms, but that's a pretty flabby explanation.
And we were hoping that the tool, a lot of times the citations, a paper that should be cited but didn't get cited, is because for the authors probably don't know the paper exists. So we are hoping that by making the tool of discovery better, we can actually help both the authors as well as the reviewers to actually point it out that certain citations should have been made.
Yeah. Good. Over here.
So I'll follow up with that. Currently, the citation count is important, but also how was a paper cited? Because sometimes you cite a paper by criticizing it. Sometimes you cite a paper by saying that it's a great work. So of course, you say that the citation means that people read the paper, so it should be important. But the way it is cited is also important. But there's also more detail in the way how it is cited. I gave you an example. You know this DB scan, which recently was criticized by another paper, which got the best paper award in another conference. And this happened to be my colleague in Chinese University of Hong Kong. And what Yu Tao Xie, Yu Tao was trying to find out is whether he is the first author to find the problem with the DB scan. And there's no way that he could find it except to look at all the 7,000 papers which cited DB scan. He asked his student to read 300 papers every day, and this took like 20 days. All right. And eventually, they found one of the master theses point out that DB scan can have this n-log n, which may not be correct. That complexity may not be correct. So instead of saying that their paper found it first, they gave all the credit to that master thesis, which nobody paid attention. Okay. If the citation can be included in a way that they can make it easier for them to find that rather than manually to find, oh, they are not the first paper to find this problem, then that would be very, very powerful. So is that a direction that guys can try to help?
So we've actually looked at that problem. We have a paper in last year's, I guess it was the AAAI Big Scholarly Data on classifying citations. And we started, as I mentioned in the talk, with classifying them into key citations or important citations or not. And important citations is kind of a pretty blank distinction, but it's trying to get rid of all these throwaway citations. We also looked at, when we were doing that, on can we classify using a finer granularity, like you're suggesting. This paper is criticizing, this paper is contradicting, this paper is advancing on it in various ways. And we found two problems. One, it was quite difficult, this is in a limited study, but it was quite difficult to get intersubjective agreement. Sure, there's some extreme cases where we say it's a very strong criticism, maybe like the example you mentioned, but other cases it's much more ambiguous, particularly because people, unlike me, often use nuanced language when they are criticizing somebody, so it's not always apparent. And it was difficult to obtain high quality label data. So we kind of backed away from that. So the summary of what I'm saying is I think it's a wonderful problem. We have started to look at it. Where we got stuck is on getting large amounts of label data where there's strong intersubjective agreement.
I will add that there is David Schotten at Oxford and other people have been working on this citation typing ontology, CITO, which has been used by some people to attempt to do that sort of analysis of citation context with the same results. I mean, it's very difficult to go from the cagey language that humans tend to use when criticizing.
So one of the earliest papers on this was by Teufel at I think at Cambridge. She actually tried to come up with an ontology and at one point tried to populate those ontologies. But it was interesting. I mean, but you know, she raises these kind of issues as a throwaway citation. I do have to respond to DB scan. I think one of the problems in DB scan was that no one could come up with a good distance function. But if you learn the distance function, DB scan actually works fairly well. So not many people have ever learned the distance function, and that's what we've been doing, is learning the distance. And there are other people now doing this too, where you learn the distance function, because it's been known that it wasn't working very well until you do something like that.
Yeah, I guess the only challenge is DB scan cannot work on big data, large data, but actually DB scan still works in some other data. Yeah, and also actually before in 2009, we also have a paper about how to classify the citation relationship. For example, we can say why is this paper cited another paper? The reason is that this paper is a series of this paper, or this paper is just some kind of similar algorithm on the same problem. We can classify that, but actually this problem is still very challenging. The quality is not that good, so it's really challenging.
So first, I want to thank all of you for building these systems and making them available to us, and also making effort to further improve them. I've used all the three that are already here, and I'm looking forward to using your Semantic Scholar later. So that's wonderful. Two questions. One is, have you looked into your search logs to understand what are some of the typical search tasks? I'd imagine, for example, some people are doing no-item search. I know this paper or this person that I want to get to, and the target is to find this person or this paper. Another kind of task that I can imagine could be learning. I want to learn about the topic now, or learn about the certain community. So that's number one. And number two is, it seems that a lot of work that you presented has been taking a data-driven perspective. So you start from the data and the information and see what we can do, and you can imagine some needs. I wonder if you have thought about taking a different perspective from users' perspective, which is us researchers, and to think about the task-driven approach. So one example is, for example, one task in research is to, to think about the interesting research question, right? So I can easily imagine one way to extend all your systems to, let's say, look into the future work section, and then classify sentences into whether the sentence is about the future direction. And then allow me to search, let's see what are some future directions in deep learning, and then just match deep learning with those sentences. This is an incremental extension of the system, but that can be very useful from a task perspective. So just these two questions.
So the first one is log.
The logs. So we've actually published a paper on how, by looking at our logs, we can discover, poor metadata extraction. When a paper just so happens that it's downloaded a lot, but it's not coming up in the it's not coming up in the search logs, then that paper has actually had poor metadata, and we've used that to improve our metadata. So you can use your logs for different things. You can also, one thing that we tried to look at, maybe you've done this, is we tried to look at deadlines for conferences to see whether we saw any trends in certain types of papers, but we didn't find that. So,
but can I just, sorry to interrupt, but it seems like you're answering another fascinating question, which is how can we use our logs to improve our systems? But the original question, which is one that I'm also fascinated by for my colleagues who have users, is when you see people coming to use the systems, particularly, right, these systems are very rich. At the end of the day, what are they using them for? Like I said, is it known item searches? Is it, so what would you say are the kind of 2-3 most popular types of queries to CiteSeer?
So for CiteSeer, the most popular query is no query. It's a direct download of the PDF.
Yep. Right, from Google Scholar, but
Google Scholar.
If we factor those out.
So if we factor those out, the most popular are usually paper names and author search.
Right. That's what we found too. And so, typically it's a partial title or a name. But we are working with Bing. That's a generic search engine. So when you type people's names, you see other information. So we actually see paper by so-and-so. It's actually frequent. Actually, if you go to Bing today, you type paper by, you already see the query completion, which is indicative of how popular that kind of queries are. But we actually want to take this opportunity to evangelize actually more additional functionality. So you can search by field of study, you can search by venue, and these are not the capability that exist in the commercial engine. So you typically don't see those in the logs because, when you try a few queries, the search engine doesn't work. The users are quickly self-trained to avoid issue those queries. So that's actually a caveat of using logs to predict what the user might want to do. So that's the first question.
Okay. I have 2 points. So the first one is that, in AMiner, so the most typical query is some kind of simple query, like data mining, machine learning, and the user actually want to find some authors, for example, experts. Like some students want to find the expert from United States and to apply PhD or something like that.
Yeah.
And some other, editor want to find the reviewers. Actually, this is very typical. They just want to find reviewers Because you will say that find the reviewer is very easy, but actually it's very difficult because, for example, every year I handle some 100 papers. So every time you cannot imagine that you just always find some friends to review those papers. You have to find some other people. You have no idea about those people, but you have to do that because you cannot assign all the paper to friends. Okay. So yeah, that's the first point.
So I have to ask, sorry to interrupt, but so if the use cases are people wanting to apply and editors looking for reviewers, do you support the right to be forgotten?
Okay. And that's actually our pain points too. And in addition to finding reviewer, they also want to resolve conflict of interests.
Yeah, actually, it's very interesting.
And so that's one of the motivation behind why we do this. So if you want to find reviewer for for a particular subject, you just typically find it famous authors. So in this new world, in this new capability we bring on, you can say paper about this subject by, and then it will suggest a bunch of users. And you can actually first say, well, this target paper is from CMU, so you add a keyword from, and then you actually list all the affiliation from the authors. So that's not directly resolve the conflict of interest, but nevertheless, it's a tiny step toward improvement.
I think we're going to go to just one last question.
I'm sorry, I interrupted him, so I wanted to give him a chance. He had another point.
I'll quickly go through. Okay, so actually this function, we have the reviewer suggestion function. Actually, this function has been used by NSFC, that is Chinese version of NSF, so which actually demonstrated the useful of this function. So, and the second point is that actually I very much agree with Chen's point. So we should focus on some kind of task. I mean, task-driven for academic research. We should not just search person, search author, and search. Actually, I don't think the student want to always search some paper and search conference. For example, I can imagine, okay, if a student already knows the, for example, data mining field, and I guess that he always knows the conference deadline and some other information, he will not search for the, okay, I want to find some best conference in data mining. No, I don't think so, right? So I guess that these are some tasks, like they always want to be keep informed by some, for example, papers published recently or related to his research or something like that. But anyway, I agree with that point on the task-driven.
Right. Yeah. So we are probably not that ready to do the future section, to help people write future section. But I think we can, to help authors to write related work section, is probably easier.
Something else that would be interesting is because CiteSeer shares its software, and so it has versions of it running other places, it'd be interesting to see what they do. Like there's a version running at the Qatar library. There's a version running at, and they're sort of independent groups. They do what they want to do. They've indexed their own things. It'd be interesting to see more than just what happens with us, but what happens with a lot of these enterprise search systems, which are like us, which are there's also one at University College London. So it'd be interesting to see.
Right. All right, we're going to have to...
So since we're running out of time, so I have one final question since I'm the session chair. So I have the privilege to ask a final question to all of you, and I hope you can give us some very short answers so that everybody takes some way. To wait. So this is also the answer. Okay, that's not the answer I want. So, but I mean, you all have your fantastic Scholar search engine. So this is also something we're trying to ask ourselves on a daily basis to push our innovation. So, if there's one thing that you want people to use your search engine, what that would be. So just give us some summary that why would people use your Scholar search engine over all other three plus Google Scholar? So I want you to answer this question in a very brief summary so that everybody, when they walk back, they want to know that, okay, in this situation, I should use CiteSeer. In this situation, I should use AMiner and something like that. So starting from you.
So right now, CiteSeer is letting you search information which is usually not available in Google Scholar because we're going inside documents and pulling out tables and figures and equations and algorithms. And not that we've done that completely, but I think that's fairly unique to us so far. and I think others are going to do this too, because it's really valuable data for a lot of researchers.
Fantastic.
Very briefly, you want to use Semantic Scholar to reduce information overload. So a lot of places will give you more, we'll give you less, but hopefully the very best stuff.
Nice.
I see. And for us, we want to promote the discovery of more content. So if you want to read more, or you want to cite more, or if you want to ding your paper's authors to not citing more, please use us.
Okay, so far for AMiner, I guess expert friendly. So, but in the future, we are working on some kind of social function. So in the future, we hope that everyone can use AMiner to store your paper and to promote your paper and to publish your paper.
I'd just like to say we're all very complementary here in many ways.
We
right?
should make our into one gigantic
Tomorrow.
tomorrow.
Okay, so thanks everybody for coming to the session. I think that's it. And remember, tomorrow we have a workshop, and from 10?
From 9 till 3
From
tomorrow.
9 to 3. So I hope I'll see you there.